All right, Fred, have you ever gone and visited somewhere where, or maybe not just visited, but lived in a place where it's really snowy?
Yeah, I served my mission in Idaho. Well, one of them.
You served many missions?
Well, I can't remember where I served all my missions, so I just, every once in a while I say I served a mission there.
That's good, that's good. So when you were in Idaho serving your mission, what do you remember about the snow on the roads?
Um, it was really snowy, yeah, there's lots of snow, yeah.
Did you ever see people try to melt the snow by adding a chemical or something?
Oh, yeah, we would there would be salt. Underneath our apartment building, there was a big bucket of salt, and we could distribute that salt on the sidewalks, and that salt melted the snow somehow.
All right. So what that salt does is it comes in contact with some of the snow, which is water, and it begins to dissolve just ever so little amount because, salt doesn't like to dissolve in cold water. But once that water that comes in contact with the snow does dissolve, it changes its freezing point. It changes the point at which that water freezes as snow, and now it becomes water instead of ice or snow. And once that occurs, then more of the salt can be dissolved, and more is dissolved, and the concentration of salt spreads to the surrounding water or ice and creates or changes the freezing point of that ice and makes it water. Okay? So, short story, you put salt onto ice and it melts the ice. Now, the hard thing, hopefully everybody's kind of aware of that or familiar with that to some extent. But the hard thing to kind of conceptualize is this question. When I put salt onto ice, it shifts the melting point of that ice. Does it lower the melting point of the ice or does it raise the melting point of the ice?
Well, the ice melts, right?
That's right, the ice melts and the temperature of the surroundings hasn't changed. So if the temperature hasn't changed and the solution, the resulting solution of water and salt now is liquid, it's not frozen, it's liquid, can I freeze that solution?
I guess not.
No, you can freeze it. You just have to get it a lot more cold. So there's ocean water up on the poles of the earth, and they're frozen. So you can freeze salt water, but you just need to get the temperature lower than regular tap water or deionized water, water without salt in it. Okay? So when we add salt to ice, the ice melts because the salt has lowered the freezing point of that water. Okay?
Lowered the freezing point.
That's right. It's lowered the freezing point. The resulting solution of salt and water can still freeze, but the temperature needs to come way down for that resulting solution to freeze. And we call this a freezing point depression. Freezing point depression. The change in temperature of the pure substance minus the change in temperature of the change in temperature equals the pure substance minus the temperature at which the mix freezes. All right, this is the shift. And that change in temperature is equal to not molarity, not mole fraction, but molality. Molality times a constant for the number of ions or particles that are released upon the dissolution of that compound. Okay? So, for example, and also the boiling point is also shifted when you add salt to water. All right? Now, when I was a kid, I heard that you're supposed to put salt into your spaghetti before you boil the water because it will make the salt or the spaghetti cook faster because salt water boils at a higher temperature. All right? Now, it turns out that that's probably not the amount of the rate at which you cook spaghetti in salt water is probably very similar to the rate at which you cook spaghetti in regular water, because you haven't shifted the boiling point drastically when you add that salt. But that little idea helps me remember that when you add salt to water that you're going to cook noodles in, you're raising the boiling point of that water. So adding salt or a solute, doesn't need to be salt, it could be sugar or any soluble solute, to a solvent will increase the boiling point and decrease the freezing point. So here we have an example. This red line here is the solution. The blue line here is the sample, the water without anything added. And the red line is once we've added a solute to our water and created a solution. And you see here is solid, and here is, let's see, high pressure, low temperature. So this is a liquid here. Here is our gas phase, low pressure, high temperature. So we have our solid, our gas, and our liquid. And if we're going from solid to liquid, and we add salt, you can see how the new freezing point over here to the left has lowered compared to the freezing point on the right. But as we go from boiling our solution from liquid to gas, we have to increase the temperature for that boiling to occur. All right, so this is the phase diagram again, and we're looking at how adding solute to water shifts the freezing point and the boiling point of a resulting solution. So here are the constants associated with the boiling point for the different compounds that you might put into different, in this case, solvents into water. And here is the K for the freezing point, how it shifts the freezing point in these different solutions, or using these different solutes. So here's an example of how we use this. The freezing point for a 40-60 solution of our antifreeze is -4 degrees Fahrenheit or -20 degrees Celsius, and we want to know what the molality of the solution is. Well, the shift in temperature equals the molality times the constant for the freezing point here in this case, right? And the constant for the freezing point, 1.86, is from water. We're freezing water here, 1.86. And the change in our solution's freezing point, well, the solution freezes at -20 degrees Celsius. The water by itself freezes at what? Do you know what water freezes at?
Well, that's a 0.
That's right. So the change here would be 20. 0 minus the -20. So we have 20 for our change in temperature. And we want to know the molality. Is that what they're asking for? Molality. And we have 1.86 degrees Celsius for every molality. All right? So 20 divided by the 1.86, that'll tell us a necessary molality, 10.8, to, or rounding up to two significant figures, 11, to create a solution which is negative, has a freezing point of -20 degrees Celsius. Okay? So, if the antifreeze mixture, if 100 milliliters is known to contain 42 grams of antifreeze and 60 grams of water. 42 grams of antifreeze, 60 grams of water. What's the molar mass of the compound found in the antifreeze if it has a freezing point of -20 degrees Celsius? Well, what we are basically going to be using here is the molality again, and we can find 100 milliliters is known to contain 42 grams of antifreeze, 60 grams of water. We know that, again, 20 here, 1.86 here, all right? And our molality is 10.75. And with that molality, we know that that means moles of solute for every kilogram of solvent. And if we know we have 60 kilograms of solvent, then we can identify how many moles of solute there are. And from that moles of solute, we can use the 42 grams of solute and identify the grams per mole. So 42 grams for every 0.6452 moles, that gives us our 65 grams per mole, and that's the molar mass of the solute. Okay. What will the boiling point of this solution be? What will the boiling point of this solution be? Well, the boiling point, does it increase or decrease when you put a solute into the solution or into the solvent?
The boiling point increases.
Okay, the boiling point increases. So what should the boiling point be?
For water,
That's right, the boiling point for water.
100 degrees Celsius.
Very good. So we go back up here to our boiling point. We're talking about water. 0.51 degrees Celsius for every molal. 0.51 degrees Celsius for every molal. And we identified the molality already as 10.75. That's my molality. And I already forgot that constant. I have to go back here to it. 0.51 degrees Celsius for every molal. What will the boiling point be? I forgot again. 0.51? 0.51. 0.51 degrees Celsius for every molal. All right. And this will tell me the change in temperature in the freezing point. So if I take my molality times 0.51, 5.48 is not my new boiling point, but my shift in my boiling point. So what did we say the boiling point of water was, or do you remember?
Oh, it's 100 degrees Celsius.
Very good. So 100 plus the 5.48, and that will be my new boiling point for my solution, my resulting solution. Okay, very good. Good place to stop.